Okay, so we're going to move on, continue working on variable acceleration, but looking at the function that calculus plays in it, so differentiation and integration. I am going to do it slightly different to the book in terms of it has two different sections for the differentiation or use of. It has differentiation and then max and minimum, but I'm doing that all in one go because to me that's really important to do together. I don't think the way the book approaches it is the best way, which is why when I'm doing these videos it's important that you're following my PowerPoint alongside. So, if I have a displacement function, s in terms of time, and I know that velocity is the rate of change of displacement, how could I express Vt? Well, if it's the rate of change, it's the change in displacement with respect to the change in time. So velocity is the derivative, which we can always write like that, of displacement. Then again, if I have a velocity function in terms of time, and I know that acceleration is the rate of change of velocity, so it's the rate at which velocity is changing over time, then I know that acceleration is the derivative of velocity. And these bits of information are really, really important for this problem, or for this section. So, I'm going to do two examples for differentiation. One from the minimum maximum chapter and one from the other chapter. So, example 1. A particle P is moving on the x-axis. At time t seconds, the displacement x meters from O is given by x equals t to the power 4 subtract 32t plus 12. So the first thing I'd do for this problem is I don't like the fact that I've got a function called x. I know that x is displacement in terms of time because it says at time t seconds the displacement x. So I want to write it in this way. So I'm going to write it out before I even start the question. You can do this in the exam as long as you are defining how you've changed it. And I think this is much easier and makes a lot more sense. So find the velocity of P when t is equal to 3. So if I know displacement, well, I know that velocity is the derivative of displacement. So I need to differentiate t to the power 4 minus 32t plus 12. So it's just polynomial differentiation using standard differentiation rules. So velocity is 4t cubed minus 32. I want to know the velocity when t is equal to 3. So you can see why I've kind of changed this function notation. So 4 multiplied by 3 cubed, subtract 32 on your calculator. 76 metres per second is the velocity when t is equal to 3, so at 3 seconds. Find the value of t for which p is instantaneously at rest. Well, the moment that something is at rest means that its velocity is 0. So 4t cubed minus 32 is equal to 0. 32 is equal to 4t cubed. 8 is equal to t cubed. So therefore, t is 2 seconds. So at 2 seconds, that is when the particle is instantaneously at rest. Part C. Find the acceleration of P when t is 1.5. Well, I know that the acceleration of t is the derivative of velocity. So my velocity function is 4t cubed minus 32. So 12t squared is my acceleration function. And I want to know what the acceleration is when t is 1.5. So 12 lots of 1.5 squared. Put this in my calculator. And the acceleration at that point is 27 metres per second squared. So straightforward, really quite straightforward problems. It's just that underlying knowledge of this case, okay? Of deriving displacement to get velocity and deriving velocity to get acceleration. So second example on differentiation before we move on to integration. So a child is playing with a yo-yo. The yo-yo leaves the child's hand at time t equals 0 and travels vertically in a straight line before returning to the child's hand. The distance, s metres, of the yo-yo from the child's hand after time t seconds is given by s is equal to 0.6 t plus 0.4 t squared minus 0.2 t cubed. For t is greater than or equal to 0, less than or equal to 3. Justify the restriction that t is greater than or equal to 0, less than or equal to 3. So what we can't say is just the comment, well, clearly that's the time from which the yo-yo leaves the hand and then returns to the hand. That is not a justification, even though factually, contextually, that is probably the right thing. We have to justify it using the function that we have. So if we're talking about distance rather than displacement, then s has to be greater than or equal to 0. We can have negative displacement, we cannot have negative distance. So therefore, I know that this function has to be greater than or equal to 0. So what I would do is sketch my graph. Now in order to sketch my graph, I need to know what my roots are. So I'd put this into my polynomial solver to find when it's equal to 0. So the roots of this graph are when t is equal to 1, negative 1 rather, 0 and 3. So we are sketching the graph as it actually is drawn as a graph. It's a negative t cubed, which means its overall shape is like that. So it's going to come down through negative 1, back up again through 0, and back down again through 3. So if this is s and this is t, I can draw two bits of information from this graph. I know t has to be greater than or equal to 0 as motion starts at t equals 0. So therefore I'm not interested in any of this side of the graph. You can obviously cross it out, but you don't have to. I also know that s is negative when t is greater than 3, and I know that s has to be greater than or equal to 0. So therefore the full restriction is that t is greater than or equal to 0, less than or equal to 3. So that's part A. Sketching graphs is a really, really useful skill in a lot of situations, and particularly in these kind of situations where you need to justify a restriction. It's quite regularly to do with the graph or visually seen on a graph. So part B, find the maximum distance of the yo-yo from the child's hand, correct to 3 significant figures. So I want the maximum of my distance function in terms of t. If I want to find a maximum, this implies when the derivative is equal to 0, i.e. when the velocity function is equal to 0. So you could kind of approach this problem without even knowing this, as long as you know that if you're finding a maximum point, you're finding the derivative of the function and when it's equal to 0. So the derivative of st is 0.6 plus 0.8t subtract 0.6 t squared. So I want to make this equal to 0. And I will solve this on my calculator to find when it's equal to 0. It is possible that you will have multiple answers. Generally, one will be negative and one will be positive. If not, then you know that there'll be a maximum that is between the range of t is greater than or equal to 0, less than or equal to 3. So it'll be within this domain. Sorry, my phone's ringing. I'm not going to start the video again. I'm just going to let that ring. So it needs to be within this restriction. And actually what you end up with is that t is equal to 1.8685, etc, etc, etc. Now, the question is asking me to find the maximum distance. It's not asking me to find the time when the maximum distance occurs, which is what this tells me. So I need to substitute that in to find the maximum distance. So I'm going to substitute this number into my displacement function, which is what this notation means. I don't need to write out 0.6 plus 0.8 times 1.86 blah blah blah. I just need to write this down because it shows that I'm substituting that in. I've put ... because that implies to the examiner I'm using the full number, or at least more significant figures than this. If you only use these significant figures, so 5, because my answer needs to be to 3, that would probably be fine. But it's always better to use the most accurate answer that you can do. And that, to 3 significant figures, is 1.21 metres. So differentiation as an approach to these problems is really, really important, even when I don't actually need to know that the velocity is the displacement, is the derivative, because in this case I don't technically need that information. But differentiation generally is a problem, as a process to the problem is really important. So we'll go straight on to integration. And so naturally, if I know that s of t differentiates to velocity and velocity differentiates to acceleration, then acceleration, if I integrate it, I must get velocity. And if I integrate velocity, I must get displacement. So the integral of acceleration is velocity, and the integral of velocity, obviously I should be writing this better and actually put it with respect to t, is equal to displacement. So ignore my lazy notation, you should have dt there as well. So this fact, it kind of makes sense based on what we've already learnt before. So we're just going to go straight onto the examples looking at this. And we have 2 examples looking at integration. So example number 1. A particle is moving on the x-axis. At time t equals 0, the particle is at the point where x equals 5. Now I might be inclined to sketch this problem, actually indicating that that is where the particle is at t equals 0. Okay, so it's worth drawing that just to give yourself an idea of what's happening. The velocity of the particle at time t seconds, where t is greater than or equal to 0, is 6t minus t squared meters per second. So that is the velocity. I've made that really quite dodgy, but velocity in terms of time is 6t minus t squared is the function. So find an expression for the displacement of the particle from 0 at the time is t seconds. Okay, so that means we need to integrate our velocity function to get our displacement function. So I'm integrating 6t minus t squared with respect to time. And that will give me my displacement function. So 6t squared over 2, subtract t cubed over 3 plus c. So let's simplify this first. 3t squared minus 1/3 of t cubed plus c is my displacement function. Now, of course, I don't want to leave it with a plus c in it. I actually want to find the function. Well, I know when t equals 0 that the distance from the origin is 5. Okay, so our displacement function is the particle from the origin, not from its starting position. And we already know that the particle is 5 spaces from the origin. So if I were to substitute this in here, that would be 0 and that would be 0. So therefore, c would be 5. And therefore, our displacement function would be 3t squared minus 1/3 t cubed plus 5. Part B. Find the distance of the particle from its starting point when t is equal to 6. So we have to read that it says from its starting point. So s of t gives me the displacement from the origin. So at 6 seconds, the displacement from the origin is what I would do substituting that in. So 3 lots of 6 squared minus 1/3 of 6 cubed plus 5, which is 41 metres. Now I already know, so from the origin it's 41 metres. I know that my starting point was here, so I only want that distance. So therefore from its starting point is 36 metres. Now, obviously, if you just hadn't done the plus 5, you would have got that value. But because we're dealing with displacement, I could have got a negative answer, which would mean that my answer was over here. So it's not actually going to give me the distance because it's going to give me a negative number. So by doing it this way and doing it as a visualising problem, it makes it easier to actually work out the answer and not make mistakes with negatives. Okay, so one more example on integration, and I'll change my colours. I'll go blue. Example number 2. So a particle travels in a straight line. After t seconds, its velocity is given by 5 minus 3t squared, where t is greater than or equal to 0. Find the distance travelled by the particle in the 3rd second of motion. In the 3rd second of motion does not mean that t is equal to 3, because it means that a period of time has lapsed. So the 1st second is between t is 0, t is 1. The 2nd second is between t is 1 and t is 2. So the 3rd second is between t is 2 and t is 3. So we've got a boundary integration question. When we have boundary integration, it is vital that we sketch. And in this particular example, it will show you why that is the case. So if I'm sketching a graph, I'm going to want to know what my roots are. Now I know that I'm only looking between t is 2 and t is 3. So actually all I'm going to be worried about is one of the roots when I come to sketch this problem. And it's because my graph looks like this. So my root is 1 point something. I actually didn't write it down when I prepped this example because of where I knew that the section was. So distance is positive. The integral I will get between 2 and 3 here will be negative. Integration tells us about the relationship between the curve and the x-axis, and it tells us about how much of that graph is actually underneath the x-axis. That's why this is negative, because it's underneath the x-axis. So I have to sketch to know whether I'm using the positive or negative version of my answer. And also because if it asks for the second section of motion, for example, so 1 was here and 2 is there, I would be working out between 1 and this root, and then this root and 2 separately. If I just integrated between 1 and 2, it's going to give me the totally wrong answer. Okay, so sketching is so important to know, 1, whether your answer is negative, and 2, whether you need to split up your problem. Fortunately, in this case, we don't need to split it up, but we do need to find the modulus of our answer. So the modulus simply meaning the positive or the absolute version of our answer. So I've done this by hand. Because it says find, you could technically just put all this on your calculator, but I'm going to revise integration as I'm going along with it, because I just think that's quite important. So I want the modulus of this between 3 and 2. I will have tidied this up when I do my next step of working, but in case you can't see, 3t cubed divided by 3 is obviously t cubed. So substitute in my upper bound. So 5 times 3, subtract 3 cubed, take away 5 times 2 minus 2 cubed. So all of that is being modulus, which is totally not a word, but it's the absolute value of that result. So 15, subtract 27, subtract 10, add 8. So I want the modulus of negative 14, which is 14 metres itself. Okay? So this is why sketching is just so important. With integration problems in particular, but generally is really important. So make sure you're sketching these graphs. So I'm happy for you to actually go away and do a mix of the sections between the differentiation and the integration ones. The actual integration you've got in year 1 obviously is going to be based on your polynomial. Next year, if they do variable acceleration problems, they'll probably use slightly more complex integration and differentiation. Obviously, you're not at that level yet, so all of the ones in the book will just be polynomial, and it will just be you guys getting used to the process of when to differentiate and integrate. Hopefully that's helpful, and hopefully the sketch, the visualisation of it is really useful for you as well.